All right, yay, new unit, yay, last unit of the year. This is about probability. I know you're probably going to ask, well, why is this in geometry class? Like, how is this geometry? Well, the answer is it's kind of not geometry, but it's in the geometry course because a lot of smart people thought we needed to do more probability and statistics throughout high school. So they put some probability and some statistics in at least once a year, every year in high school, and geometry gets probability. Now, there's a time in the middle of this unit when it makes a whole lot of sense why we got probability. And I think, yeah, it also makes a lot of sense that there's a little bit of stats and low probability in everybody's math class. Okay, so this one is probability. It's ours. It's the last one of the year, and it's maybe quite possibly the most fun unit of the year. Okay, so what is probability? We're going to talk about today what theoretical probability is in general and how to make a sample space. This is most closely related to section 13.1 in the book. It's not exactly section 13.1. We have a little more than what's just in there. We thought the stuff in 13.1 was a little bit basic and really doesn't set you up very well for the rest of the unit. So this is kind of 13.1. This is kind of 13.1 plus some other stuff. Okay. Represent sample spaces using tables, lists, and tree diagrams. Hopefully you've done some of that before. Fundamental counting principle, and probabilities of simple events. Okay, an experiment is a situation involving chance that leads to results called outcomes. An outcome is the result of a single performance or trial of an experiment, and an event is one or more outcomes of an experiment. That's just kind of some vocab at first. If you're going to flip a coin, that's, just by itself, that's a trial. But if you're going to flip two coins, perhaps, then that whole thing is called an experiment. I think is the way that means. You know what? These kind of terms, you get really mixed up in the technicalities of them, and then you realize you never need them again. So it's good for setup, but we're not going to ask you which one's the trial, which one's the experiment on the test. And I don't think having that sorted out perfectly is going to help you actually do the test anyway. Sample space, this is something you do have to get used to. A sample space is the set of all possible outcomes. So tossing a coin a minute ago, the sample space on tossing one coin would be the list tails, heads. That's the entire sample space for flipping a coin. Sample space for rolling a six-sided die is all of the outcomes just listed, 1, 2, 3, 4, 5, 6. Sample space for, sometimes they talk about stuff like flipping a thumbtack. A thumbtack is one of those things that's sharp and pointy, and it looks like it has a place you push your thumb on the thing and then a tack that goes into the wall. The sample space is, well, it could land so that it's pointing straight up, or it could land so that it's kind of like on its side like this. So that has two items in the sample space. Okay, you can make a list, you can make a picture, you can make a tree diagram, you can make a table. Tree diagrams are probably the newest to you at this stage. We'll do one of those today. If we were to roll a six-sided die, okay, I said that already, and that's it. One stage. If we were to roll two dice, it gets a little more complicated. We'll get to that later for sure. Experiments can involve multiple stages, and when this occurs, the numbers of outcomes can increase, and the practicality of listing them is crazy. So to find the number of possible outcomes, we can use the fundamental counting principle. Okay. The number of possible outcomes in a sample space can be found by multiplying the number of possible outcomes from each stage. So if we were going to roll two dice, your standard six-sided die, roll one has 6 outcomes, roll two has 6 outcomes. If we were going to roll that one die twice, how many ways can this whole thing turn out? The ways that can totally turn out, there should be 36 ways that could possibly happen. If you're going to flip two coins, well, the first coin has 2 ways it can turn out. The second coin has 2 ways it can turn out. So we're going to have 4 possible outcomes. If you had a coin and a die in your hands and you were going to do all that at once, flip a coin and roll a die, there would be 12 possible outcomes. So that's just what this is saying here in symbols. In a K-stage experiment, so if it has K stages, you multiply all the possible ways each stage can turn out. All the way up to the last stage. When you multiply all those, you'll find out how many outcomes there can be. You'll basically find out how long is that list of the sample space when you do that. In any given experiment, of course, results may vary. You might get 2 heads in your coin tosses. You might get a 3 and a 6 in your die rolls, but they're not always the same, of course. If we were to toss a fair coin 6 times, we may get 3 heads and 3 tails, but we might not. Experimental probability gives the ratio of desired outcomes to total outcomes. So let's do it this way. An experimental probability, you actually run the probability. What you do is you actually roll the dice a bunch of times and you see what happens. And you want the experimental probability of getting exactly 3 heads and 3 tails. You'd say you try flipping the 6 coins, 1,000 times, and count how many times you got 3 heads and 3 tails out of the 1,000 times that you tried. So this would be like number of times that it favorably happened, or it happened the way you wanted it to, or it happened the way the way it would be successful for the thing you're trying to find the experimental probability of, such as 3 heads and 3 tails. So how many times it happened that way out of the total number of trials, total number of times you flipped the coins or something. So that's why we're saying it's a ratio. Probabilities are always these kind of ratios, like favorable, or the way we wanted it to be, or the thing we're trying to find the probability of out of the total number of ways it did happen, good or bad. So the good over the total. Experimental probability gives the ratio of when you actually did it. Theoretical probability, okay, let me read this way. As the number of times we perform the experiment increase, and as I was to toss these 6 coins thousands and thousands of more times, the theory here is that this fraction gets closer and closer to what we would call the theoretical probability, the measure of chance of an event occurring in any trial experiment. This would give us, over time, it would tend to land on the empirical kind of scientific probability that we wouldn't expect. Okay, so those are 2 kind of separate definitions of probability. We're going to be dealing, of course, with theoretical probability more than anything, because we're not actually going to get out coins and dice and run all these experiments. We're going to talk about the ways they should eventually turn out if you were to do them thousands and thousands of times. All right, which is actually easier than it sounds at first, at the start. All right, the probability of an event E takes a value in the range from 0 to 1. All right, so think about that probability. Theoretical probability is the number of ways it should turn out of the total number of times you're going to run it. That fraction, the lowest it could be would be 0 if the top thing never happens out of whatever, how many times you're going to try it. The lowest it could be would be 0. The highest it could be would be 1 if it's one of those probabilities that you're sure is going to happen. If it always happens every time you run it, then these two values would be the same, and the probability would be 1. So the probability, and this is the notation for the probability of event E happening, the answer to that probability you can kind of think of as a percent, essentially, or a fraction between 0 and 1. 0 means definitely never happens and it's totally impossible, all the way up to 1, which is absolutely, definitely, sure thing has to happen. And then we have this continuum between 0 and 1. All right. When events are equally likely, the probability of them occurring is this. Probability of E occurring is the number of possible outcomes in the sample space divided by underneath, I should say, the number of ways that thing can happen. Yeah, that's gonna be easy to see as we move on and actually do some. Okay, burger time. Oh, we talked about this first. About how to make trees. Tree diagrams are useful in depicting the outcomes of an experiment and can be used for events that have equal probabilities or unequal probabilities. Okay, so you have this first example. Yeah, this is one of those things where it's going to be easier. It's just going to make more sense if we actually get it. I threw just a second. I threw something across the room. Whew, that was fun. Sorry about that. Talking with my hands. No, you can't see me. All right. So find the number of possible outcomes for someone who is going to order a burger if they are given these choices. So first of all, they get to decide, is the burger going to be a single, double, or triple? And I went and found this awesome clip art for you. Is there going to be cheese? Is there going to be pickles? Is there going to be tomato? So we could think of this as, like, each one of these bullets here is a separate decision. Which type of burger are you going to order? And you have kind of a yes or no question for the rest of these 3 things. So this is how tree diagrams work. I'll just go for it here. We'll do this in black. For some reason, they always put this, I guess because it shows branches at the beginning. At the start of this thing, and we're gonna run this kind of timeline from left to right. So here you are, starting at the beginning, and there's a fork in the road, and it has 3 possible choices at the first stage. We could either go this route, or this route. Then after we've made that decision, because I'm trying to represent here all the possible ways this whole thing can turn out. Because we're really after, what are all the possible ways something can turn out? That's going to be what this denominator is on all these probabilities. So we need to know how many different total menu choices would there be? Like how many ways could you walk out the door with this burger? Because there's so many different yeses and nos and all that stuff. All right, so the first stage you have to decide, well, which one of these you're going to go for. Then under the cheese question, let me just make this a header. Then we have the cheese question, the pickle question, and the tomato question. I hope I have enough room on this. So this is like yes or no here, yes or no here, and yes or no here. So this could go, so say we're on this path. At this point, it could go yes or no. I think I'm going to need more room than that. Whoops. Yeah, so that could be yes. That could be no. This could be yes, could be no. This one could have cheese, could have no cheese. Okay, so even at this stage, if we're looking at single, double, triple, and do you want cheese or not, there's 6 different ways. And at this point, what we're representing here is this branch, this path that got us here was someone who had a single burger with cheese. This one right here is a double burger with no cheese. I think you can kind of see that. And then you can see what's going to happen next. Then we have to talk about the pickles. This burger that was a single with cheese could have turned out to have yes or no pickles. This one could have had yes or no pickles. This one could have yes or no pickles. So we're adding possibilities really fast here. And I think I am going to run out of room by the end. They're getting really smashed together, aren't they? Okay, and then, so now at this point we have 12 different ways you could have ordered. Triple burger with cheese without pickles, that's kind of right here. And so all those different combinations are represented by each one of these paths that get you from here all the way through to here. All these are now going to turn out different. And then for each one of these, this is going to be tight. For each one of these, I hope you can tell, we're going to have 2 decisions. We're going to have 2 ways it could turn out on the tomato. Maybe I could sort of represent this. Each one of those is going to lead to the decision on yes, no, tomatoes. I'm going to go lowercase here just to make it smaller. Yes, no, yes. And all the way down, can you understand that? I think I'm going to fill those in. So how many different in the sample space there? If you look at all those events, how many little ends of all these branches are there? Well, you know what? I don't want to count those. I'm going to think about this with this rule we learned back here. The total number of outcomes is going to be the product of all those. So there was essentially 3 ways that one could have turned out. There was 2 ways that each one of those could have added 2 more branches for each one of these. Then the pickle question had 2 outcomes. Then the tomato question had 2 outcomes. This whole thing has 24, it appears. At this point we had 3. At this point we had 6. At this point we had 12. And at this point we had, 12. Okay, and at this point we had 24. So there's 24 different ways you could order your burger at this place, if those are the choices. I may have to pause the video pretty soon. Yeah, I'm just going to do this now. We'll just start part 2 with the coins. Okay, pause. Part 2 coming soon.